Okay, we're going to go back one exercise and look at, I think it's exercise 2.9, maximum and minimum values. We actually came across this in today's lesson, and I think we need to go back to this exercise, which we omitted. So with maximum and minimum values, your curve can have your maximum and minimum turning points, but they may not necessarily be the maximum or minimum values of the function. Now we're going to look at this example down here. Now in this example, obviously I have a maximum turning point at -1,6. So we call this point here a relative maximum turning point. Now, even though this is a maximum here, it's not the absolute maximum value of the graph. See, we'll notice that this graph starts down here and it goes down all the way here and further down. It goes up, we've got a relative maximum there, then we've got a relative minimum at 3, -26, but the curve continues to go up and it actually goes up, you know, unrestricted all the way up here. So there will be a maximum value somewhere up here. So since we've got a relative maximum point here at -1,6, it does not give the maximum value of the entire graph. And similarly, this relative minimum turning point down here does not give the absolute minimum value of the graph, because this graph continues down here on the left here. So there are more minimum values down there. In this exercise, we'll be restricting the domain of the curve to certain x values. So for example, if we restrict the domain of the curve to, say, from -4 to +4, so x values from -4, now -4 is about here, and the minimum will be somewhere down here when x is -4. Now that is going to be less than -26, so the absolute minimum will be less than this minimum turning point. And if we restrict the top end of the domain to +4, then that relative maximum up here will be higher than the graph is, say, down here. Okay, so what we do, you need to substitute endpoints of the graph in. So if you're given a domain, what you do to make sure you've got the absolute maximum or minimum, you need to substitute in the endpoints of the domain, as well as looking at the turning points. Okay, now, as I said, if we substitute the endpoints into the equation, so here's the equation, y = x³ - 3x² - 9x + 4. If we restrict the domain from -4 to +4, we substitute -4 into this equation and see what we get. Substitute x is -4. If we look down here, we get a value of -75. So that is the minimum value of the curve. See, at this minimum, when x is 3, y is -26. So that's just a relative minimum, whereas the absolute minimum for the domain from -4 to 4 is -75, as we got with this substitution. Now if we substitute x is 4 into the equation, we get -19, which is, so when x is 4, y is -19. This is obviously not higher than when x is -1, y is 6. So therefore the absolute maximum will be where the relative maximum is, if you're just looking at the domain from -4 to +4. Okay, so if we see that drawn down here, where we're restricting the domain from -4 to +4, you just find the coordinates of the endpoints of the graph, and we can see here that we've got a maximum value of 6, but our minimum value is -75. So we're just going to do one example from the exercise using this process. Exercise 2.9, question 7, and it says to find the relative and absolute maximum and minimum values of this function of x equals 3x to the power of 4 plus 4x³ - 12x² - 3 for the domain from -2 through to +2. So let's look at the first derivative first. So f dash x is 12x³ plus 12x² minus 24x. And I'll just do the second derivative as well while I'm here. So the second derivative is 36x² plus 24x minus 24. Now we know that for stationary points, that the first derivative is equal to 0. So putting that first derivative equal to 0, we get 12x³ plus 12x² minus 24x is equal to 0. Dividing through by 12, we get x³ plus x² minus 2x is equal to 0. We can factorize out an x. You do not divide through by x. You just divide through by 12 just to make it the factorization easier. So divide through by 12. So if you divide through by x, you will lose the solution. So we can just factor out an x, and we get x bracket x squared plus x minus 2 equals 0. Factorising that, we get x times x plus 2 and x minus 1 equals 0. So therefore, we've got that x equals 0, negative 2 and 1. So we need to see, so we've got a few stationary points there, okay? So therefore, we better find out the y values for these functions. So therefore, stationary points at, now 0, we substitute x is 0 in here, and we'll get negative 3. So we've got stationary points at 0, negative 3. We can substitute, I'll do the 1 next because that looks easier. So 3 times 1 is 3, plus 4 is 7. 7 minus 12 is negative 5, minus 3 is negative 8. And the last stationary point, we have to substitute 2. 2 to the power of 4 is 16. Might just do that over here. So when x is, sorry, it's actually negative 2. So when x is negative 2, we've got 3 times 16, that's 48. Then we've got 4 times negative 8, which is minus 32. And we've got minus 12 times 4, which is minus 48 again. And we've got minus 3, so we've got 48 minus 48, that's 0, and then negative 35. So we've got 3 stationary points, one at 0, 3, one at 1, negative 8, and the other one at negative 2, negative 35. Now we can obviously see that, yes, we might have, this is more than likely going to be a minimum. We need to look at the second derivative to determine the nature of the stationary points. So when x is 0, the second derivative is 0 plus 0 minus 24 is negative 24, which is less than 0, which means concave down. Therefore, we've got a maximum at 0, negative 3. When x is 1, the second derivative is, substituting that into there, we get 36 plus 24 minus 24, which is 36. And that is greater than 0, therefore concave up. Therefore, we've got a maximum at 1, negative 8. So I'm just running off screen there. And these are relative maximums. So we've got a relative maximum. Sorry, concave up is a minimum. Sorry about that. Concave up, we've got a relative, oh, that's not working. So we've got a relative minimum at the moment at 1, negative 8. And when x is negative 2, the second derivative is 36 times 4, that's 144, minus 48, minus 24. So 144 minus 48 minus 24, I think is 72, which is greater than 0, again concave up, and we've got a relative minimum at negative 2, negative 35. So I'm just going to draw what we've got so far. Oh, we also need to, before we go any further, we want relative maximum and minimum values in the domain negative 2 through to 2. So we're just going to, well, we know when x is negative 2 that y is negative 35. So we've already got that end point. We just need the other, so the other end point is when x is 2, y, that's my other end point. So looking at the original function, when x is 2, y is 3 times 16, which is 48, plus 4 times 8, which is 32, minus, up here, minus 12 times 4, which is 48 again, and then minus 3. So when x is 2, the other end point is 32 minus 3, which is 29. So 29, sorry, is an end point. And so the other endpoint is minus -2, -35. So now I'm going to sketch it. Okay, so we've got, sorry, it's looking a bit messy. We've got -1 and -2, 1 and 2. We don't need to go any further than that. Just a rough sketch. I might just say, well, 29 is roughly up here. So I'll call that 229. When x is 1, we've got a minimum at 1, -8. So these are our points. We've got 229 as one of my endpoints of my domain. I've got 1, -8 as a minimum. When x is 0, y is -3. So at 0, -3, I've got a maximum. So here, at 0, -3, we've got a maximum. At -2, -35, sorry, we've got another minimum. So -2, -35, somewhere down here, we've got another minimum. Now, we don't need to go further than that. I'll just dot that. That is a minimum. So here, this is in the domain from -2 to +2. We have an absolute maximum at the point 229. We have a relative maximum just here at 0, -3. We also have a relative, so that's a relative maximum here. So a relative maximum. This is my absolute maximum. I have a relative minimum, which is just an ordinary minimum, at 1, -8. So that's my relative minimum. And here I have an absolute minimum at -2, -35. So therefore my absolute maximum equals 29. My relative maximum is there. My relative minimum is there, and my absolute minimum value is -35. Okay, so the absolute minimum occurs at -2, 35, but the absolute minimum value is -35. The absolute maximum value is 29. Okay, we've also got a relative maximum of a relative maximum value of -3, and we've got a relative minimum value of -8, but it occurs at 1, -8. But the relative minimum, so whenever you're talking about minimum or maximum values, it refers to the y value. Okay, so you can say it's at that point, or the absolute maximum is that value. So you're better off saying that it is that value. The relative maximum is -3 there. There's a relative minimum of -8 there, and the absolute minimum value is -35 of that curve. Another example, exercise 2.9, question 9. Sketch y equals the square root of x plus 5 for -4 is less than or equal to x is less than or equal to 4. So the domain is from -4 to +4, and find its maximum and minimum values. Now, we're not going to differentiate this, because you should really recognize this as a half of a parabola. So if I square both sides, I get y squared equals x plus 5. So you know how we've got x squared equals 4ay, and we've got y squared equals 4ax. So remember, x squared equals 4ay is, or a y equals x squared, so I don't even have to think of it like that. A y equals x squared parabola looks like this, okay? And an x equals y squared parabola looks like that. So therefore this parabola here is x equals y squared minus 5. Now that, what I've done here, I've squared both sides to find out where this original parabola came from. We did this when we did the functions topic earlier in the year. So if you know that this, you're not sure if it's half a parabola or half a circle or whatever, you square both sides, and you'll see this, y squared equals x plus 5. Take this 5 to the other side and you get x equals y squared minus 5. So this really is a parabola. This bit is a parabola. sideways turn parabola, it's x equals y squared shifted back 5 units. So the whole parabola is like this. That is x equals y squared minus 5. But if you just want y equals the square root of x plus 5, it's only the top half. So if you just want the top half, this bit here is y equals the square root of x plus 5. Whereas this graph here is x equals y squared minus 5. Okay? Sorry, that's not working. So therefore, we're sketching that for -4 to +4. Now I've started from -5. So if you want from -4, it would just start here. So what we're going to have to do is delete this little bit here and work out its endpoint. But I'm going to keep it, just maybe have it dotted there at the end so that you know what the original function looked like. And you can just have it dotted down that end, okay? So but better work out the endpoints. So when x is -4, y is the square root of -4 plus 5, which is the square root of 1, which is 1. So therefore this point here is -4, 1. And when x is +4, y is the square root of 4 plus 5, which is the square root of 9, which is 3. So this point up here is 4, 3. So therefore we can say that the maximum value is the y value up here is 3, and the minimum value in that domain from -4 to +4, the minimum value is 1. Okay, now that one did not require any differentiation because there were no turning points. Okay, so because there were no stationary points or inflections for this particular curve, we didn't differentiate it. Okay, all right, now we're just going to look at one more question, which is exercise 2.9, question 10. I'll just write down what that is. Here's exercise 2.9, question 10. It is show that y equals 1 over x minus 2 has no stationary points. Find the maximum and minimum values of the curve for the domain from -3 through to +3. Look, we know that this is a hyperbola. It has an asymptote at x equals 2. It's a positive hyperbola. So we know that this, from our curve sketching, got an asymptote at x equals 2. It's a positive hyperbola. It looks like this. Okay? So that's basically what the function looks like. Now, we've been asked to show that it has no stationary points. So what we need to do is the first derivative. So we've got y equals 1 over x minus 2, which is x minus 2 to the power of -1. So y dash is -1 bracket x minus 2 to the power of -2 times 1, which is -1 over x minus 2 squared. So that's what the first derivative is. Now we know that for stationary points that the first derivative equals 0. Now if we put this here over 0, equal to 0, this has no solution because the numerator is the only thing that can be 0, because you can't do -1 over 0 with 0. So when we cross multiply here, we got that -1 doesn't equal 0. Basically, we've got no solution to this. Okay? Because -1 doesn't equal 0 and denominator cannot equal 0. Okay? So, therefore, no stationary points. No stationary points, as there is no solution to y dashed equals 0. Now we have to find the maximum and minimum values of this function. So, and we just want it between the domain of x is -3 through to x is +3. So x is +3 is about there. So we're just going to find out the values when x is -3, the y values when x is -3 and when x is +3. Now when x is -3, y is 1 over -3 minus 2, which is 1 over -5, which is -1/5. So this point here that I've got is -3, -1/5. Okay? And we know that this goes to infinity here. Also, when x is 3, we get that y is 1 over 3 minus 2, which is just 1 over 1, which is 1. So basically I don't need the rest of that. So if we look at the maximum and minimum values, well, the maximum value is going to be positive infinity, because this approaches infinity, because the line x equals 2, the vertical line x equals 2 is a vertical asymptote. So therefore the maximum value is infinity, and here on the left hand side of the asymptote, this approaches negative infinity, and so the minimum value is negative infinity. Okay, so the minimum value is not negative 1/5 or 1. Okay, the curve approaches negative infinity down here, and it approaches positive infinity up there. So therefore the maximum value is infinity, and the minimum value is negative infinity. If you could now please do exercise 2.9, and I'll just give you a couple of questions, okay? You could just do for homework exercise 2.9, questions 4, 6 and 8. Okay, I'm going to be doing another video now for another exercise, and if you can just please watch out for that a little bit later on.